Hello, welcome to the fourth and final video tutorial in the CoEDL Summer School Visualization course. In this tutorial, I'm going to return to the Pama-Nyungan subgroup data that we looked at last time in our matrix visualization tutorial. This time I'm going to see what that data looks like when we produce a geographic visualization. So, as in the last tutorial, I'm just going to be running through a set of visualizations in the workbook and talking through what the vega specification includes in each instance. To follow along with the video tutorial, you can follow the links in the video description or go to my observable site. So beta.observable.hq.com/@Lydia/Pama-Nyungan subgroups map workbook. So this workbook contains a number of maps built up as the workbook scrolls down. Firstly, we just have a map of Australia. Second, we have a map of the reported locations of some Pama-Nyungan languages. And thirdly, we've got the language subgroups, kind of roughly plotted geographically, and I'll talk a bit about that when we get down to it. And finally, we have all three of those maps overlaid on top of each other. So the basic landmass of Australia, the locations of individual languages, and the polygon areas that show which languages belong to which subgroup. And if we hover over one of those subgroups, we can see links from one subgroup to another, where a thin link represents that there are only a few word matches between the two subgroups, and a really thick line represents that there are lots of word matches between those two subgroups. So how do we build that visualization? Well, to start with, we need a map of Australia. So if we look at this cell that's called part 1, just the map, see we've got two cells. We've got one, it's just called the world, and this is our data in a format called GeoJSON. That's it's a map of the whole world. And then in our cell that's called just the map, we see our embed function that we've been using to plot our vega specifications, and then a vega specification, and it's taking in the data, giving it a name map, and pointing it to a URL to actually retrieve the data values, and that's got the variable name world. So that's typing the URL that you see up here in the word cell and feeding it into the vega specification, and then that URL property heading lets vega know that the format the data is coming in is from the URL, so that it can go and fetch those data values directly. The format of the data we've also specified, and we've said that that is of the type topo.json, which is a specific data format that is used in JavaScript object notation to describe geospatial data. And then the feature property, telling it that their features are, in this case, country boundaries. And we've got one transformation that's operating on that data set, and it's of the type geopath, And what this geopath transformation does is it takes a set of coordinates which are featured in the TOPA-JSON data and turns them into a connected path that translates from latitude, longitude data into XY coordinates. And the geopath transformation needs a property called projection, which is specified down underneath this scales property. So we know all about scales in Vega, but another property that we can add to Vega and that we need to add when we're doing geospatial visualization is called a projection. And a projection needs a name. In this case, we've just called it projection. It needs a type, and here we're using a Mercator projection, which is one of the most common geospatial projections we can use. We're using a scale to make our map smaller or larger, in this case larger than the default, and then using this property called clip extent to just show part of the map, because the data that we're feeding in shows the whole world and we just want a map of Australia, and then using the translate property to move the map around so that Australia is centered in our viewport, like so. And then to draw the map, we use a single mark type, and we use the type path, and it's taking the data from our data set, which we called map, and on enter it's encoding the fill value to be just this pale gray. If we change that to black and press shift enter, we can go up. We've changed the underlying map color. And same, if we change the stroke color, we give it a different outline color. You can see we've got a red border around it. And then to actually draw its shape, we use the property path, and we're giving it a field, and field is called path, which is generated by this geopath transformation. Automatically creates a new entry in our data set called path, a new field called path that we can use. And so those three things, our data set in a GeoJSON or TOPA-JSON format, our projection, which is translating from geospatial coordinates into XY coordinates, and then our path mark together create a underlying map shape in Vega. So this is great to be able to draw a shape on the map, but we also want to plot information on them. And to do that, we're going to use the same basic idea, these geospatial operations, transformations in our data property. I'm going to use a projection, which is its own property, and then we're going to use marks where we read those geospatial properties and use them as either a path or XY coordinates. So if we scroll down to our next part 2, then here we're showing just the locations of different languages in the Parma family. These are the locations that were reported in that data set from the paper by Booker, Bowen, and Atkinson. So I've used their locations, and the other thing that's happening with these data is some of the locations have multiple languages associated. So what I've done is whenever you hover over a language, over a red dot in the map, it will show you how many languages and the names of the languages that are reported in the paper at that specific geospatial coordinate. So how is this visualization created? Well, if we open up the observable cell, you can see once again the vega specification. So we've got our data variable is using values from an array called langs, which I'll show you in a second. And then it's doing a transformation, and it's doing a geopoint transformation using our projection called projection, and applying that projection to the fields long and lat. So our projection is the exact same projection that we used in the previous visualization. And if we scroll down to the bottom of the observable notebook to look for this dataset langs, we can see if we've got the array here, and it's a list of objects where each object has a full name, a code name, an abbreviation, the latitude, the longitude, which subgroup it belongs to, a glottolog ID, and a date and another ID that were reported in the data. And it's also got these XY coordinates. These are the XY coordinates that have been created using that vega cell that we just saw. So that geopoint transformation has taken the latitude and longitude, and it's generated an XY coordinate. So then if we go back up, and if we look at our marks, we've used the type symbol. So that's creating a circle from that data set, which we call places, which was the langs data. We called it places in this vega specification, and then encoding on enter when the mark is first created, given it a size of 100, given it a fill value of red, given it a fill opacity, so it's quite transparent of 0.3, and a white circle around the outside, but the stroke is 0, so that's not actually doing anything. And we've used our X and Y coordinate that we just talked about as being the output of our geopoint transformation. So, and here we see that same projection, the Mercator projection with a scale of 1,000 and clipped and translated to move across. Now, interestingly, we only have that one data set places. We don't actually have our world data, and that's why even though we've got the projection, we don't have any path shapes to be able to draw to create the visual image showing what that projection is doing. We're only seeing it through the arrangement of our data points. I spoke incorrectly a second ago when I said we only have one data set. We actually have a second data set in the vega specification, but it's a little bit of a sneaky data set. What this data set, which has the name selected, is doing is it's actually taking our main data set places. So here we've got this source property and says from our data set places, we're going to filter it down using a transform filter. And the expression, if the x is equal to a signal called hover x and the datum.y, so if each value of each place in our data set, if its x value is the signal hover x and its y value is the hover y, then we're going to keep that, we're going to store that place in a second data set called selected. And so what that is doing is, if we scroll down to find our signals property, our vega specification, we can see we have got a signal called hover and then a signal called hover x and hover y. And this is telling us that when we hover over a symbol, we're going to update our hover signal with the data value, so with the data value of whatever we're hovering it over, and then using that hover, we're going to define a hover x, which is normally 0, but if we're hovered over something, so if our hover is not null, then it's going to be the x value of whatever symbol we're over, and then the hover y value is again going to have a default value of 0, but if we're hovered over a symbol, then the y value of our signal hover, so that's the y value of whatever data point we're hovering over, is going to be stored in the signal hover y. So what this is letting us do is that interaction that we defined earlier. So when I hover over a point up here in the top left of the chart, we can see the languages here. And the reason we had to do it with multiple signals and actually retrieve that x and y value is that says whenever we're hovering over a point, just remember the location of the mouse and then find all of the languages, not just the one that's plotted on top, but all of the languages that have that particular xy coordinates. And then in our marks property, we have the mark, we have a couple of marks, text marks, the one down the bottom here is showing us the actual list of languages. So it's a type text. It's turned the interactivity onto false, so that means nothing will happen if we hover over it. That's a little bit redundant. And we're using that data selected, which was the filtered data from our places. And on encoding on enter, the x value is going to be 0, so that's making it appear over on the left. Our y value, we've applied a scale called list, and then using the field full name, and it's offset by 40, so it's spaced down the page by 40 pixels. And what that list scale is, which we can scroll up to find, here's our property scales, and we can have a look. A list scale is of the type band, and the type has the domain from our data set selected, so that was the filtered places data, and using the field full name, and our range, we've, instead of specifying how much space to fit the data into, what we can do with this step property in a band scale is we can just say assign each item in our domain a fixed height, in this case, a fixed size of, here we've said 20 pixels. And so what this is doing is saying in the domain, find out how many languages have been selected, and then for each of those languages, space them out, evenly spaced at 20 pixel intervals. And we've had to use that domain field full name, and so in our marks we've again used the domain. We can scroll down, full name, and that's how the Vega specification knows that this particular text mark should be spaced according to that list scale. And we've got a font size and alignment, so we have a nice text aligned list. And then on the update property, we actually assign that text, the full name, to the text mark, so we know what text to write. And then just above that, we have another text above that in the Vega specification, but also above that in the visualization, we have another text mark. This one isn't from any data, so it's only going to produce one text label for the whole plot rather than one per data item. And so what this does is it's encoded on the enter to set the position. So that's going to be an X value of 0, a Y value of 10. It's going to be black, 16-point font, italicized and over to the left. And then when we update the plot, we set the text using this test function that says we test whether our signal hover is null. If it is null, then we return the text, hover over a point to show the language name. And if this test fails, so the hover has some data associated with it, then it's going to return the text value languages. So this is creating this null value. We're not hovering over any of our symbols, so we're just getting that default hover over a point to show the language names. And then when we hover, we say that text changes to read languages and becomes the heading for our language list. So that's two elements of our map. We've got our shape, map shapes. We have our language points. The third thing that we're going to plot is our actual subgroup locations, because we saw in our language data, in our language array, we had recorded the subgroups associated with each language, but we're not actually showing them visually. So to do that is the job of the next map visualization. So I have here in the observable notebook a bunch of notes about how the shapes are created and what they mean. Essentially, what we're creating is just the smallest boundary that we can create using straight lines to enclose all of the languages in a particular subgroup. So it's just giving us a rough sense of where the subgroup sits within Australia, in particular, which subgroups is it near and which subgroups is it far away, to give us that geospatial context to be able to analyze that matches between subgroup data. So if we look at the particular data that we're using is in a file called subgeo.json, and what that looks like is, so if we look at a particular object in the array, we have each one is called a feature. It has a geometry of type polygon, and then it has some simple coordinates that are in latitude, longitude values. And then down in the properties property, we have another object, and that's telling us the subgroup name, the languages associated with that subgroup, and a set of points again, and a center point called cent. I'll just close that data up. And then if we scroll down to the next cell, we can see those polygons mapped out. And once again, we're just showing the polygons for the subgroups and a label. We're not showing the map shapes, and we're not showing the language location. If we open up the cell, we can see the vega specification has data, scales, projection again, the exact same projection we've been using. In its marks property, we have a path mark and we have a text mark. And we don't have any signals, unlike the previous map. So the data we're using is that subgeo.json file that I've shown you earlier. And we've used that as the values in a data set called subgroups. We've used two different geospatial transformations, the geopath transformation that we use to create the map shapes, and the geopoint transformation that we used to create the language locations. And the geopath transformation is really simple. It just uses that projection the same way the map shapes did. The geopoint location, previously it used the fields latitude and longitude. We've had to be more specific and drill down into the properties of our subgeo.json and said, okay, we're going to use the property called properties, and then the sub-property of that which is called cent for center, and then the first element of that array. And then the as property of our transformation says to spit out an X and a Y coordinates. So if we scroll down to our marks, what we can see is that our path mark is using the property called path. Our text mark is using that property X and Y from our geopoint transformation. So our path data is taking from the dataset subgroups, drawing a simple path using those geospatial coordinates that have been translated using that projection and the geopath transformation into an X and Y values, and filled red with again a very high opacity, value 0.2, and our text value is taken from the same data set but using the text, using the properties name, so the subgroup name, and plotting that at the X and Y values. So that's the center of the polygon transformed from geospatial coordinates into X and Y coordinates. And then some simple formatting of the text. So now we have 3 elements, a set of outlines, filled in outlines of enclosing the languages in each subgroup. We have more specific reported locations for each language. And then we have a map shape. What we'd really like is to be able to combine all 3 of these things together. So we do that in the final map down the bottom of the workbook, which if we open the vega specification, we have our data set with the name map contains that URL of the world site, specifying the format, doing our geopath transformation with our projection. We have our subgeo-JSON data, which is the values for the data subgroups, applying both that geopath transformation and a geopoint transformation to give us the name. We have our places data set with the length value, and that's been transformed using the geopoint transformation. And then finally, we have our selected data set, and then in between that, we have a data set called pairs, and a set, it's using the values submate, short for subgroup matrix, which is actually the data we used last time for the matrix visualization. I'll talk through the transformations involved in that in a little bit. I just want to run through the marks and scales that we have. So we have our projection. So the marks that we see in order are the map of Australia, that map shape path. We have a path for the subgroups, those red enclosed outlines, and then we have the symbol mark for each language location. We have a path location, which is going to show us links between the subgroups, and then we have that text, which is going to show us the subgroup location. And we still have here the text and the selected data set to show us, if we hover over a language location, what's the list of languages at a particular XY coordinate. But if we go up to the map and start hovering over sections in the map, we don't see the language names appearing up in the top left corner, even though the code is there in the Vega specification. And that's because the new interactivity, the links between subgroups appearing when we hover the mouse over a subgroup area, is overriding the language name interactivity. That's because it's important in Vega that the order that marks appear in and the order that interactivity is defined in is the order that you end up getting in your visualization. So if we were to scroll down to our marks, if we were to take the map mark out of our array and move it at the end of the text, press Shift Enter, and we can see our map of Australia has appeared over the top of all of our other shapes. So whatever we write last in the Vega specification ends up on top of our visualization view. I'll just press undo to put our map back, Shift Enter on the bottom. So now we've seen with our 3 levels of marks, the path for the map of Australia, the red polygon shapes, again using that path mark for the subgroups, and our circle symbols for the language locations. We've combined those 3 bits of information using the 3 data sets. I said earlier that there's a 4th data set in there, that subgroup matrix, and what that's doing is when we hover over one subgroup, it's showing us the word matches between subgroups. So if we go back down to where we've defined those data sets, we have that subgroup matrix data stored in a Vega data set called pairs, and there's a number of transformations that have been applied. If you remember, that subgroup matrix data has properties L1, L2, which are the different language subgroups, and then matches with the number of word matches that are shared between those 2 language subgroups. So the first transformation that's applied is a filter that checks whether the subgroup that's being hovered over has the same name as the L1 name of the entries in the subgroup matrix. So it filters just down, so we've got those ones where that L1 subgroup is the hovered over subgroup. And then it filters again, this time only leaving entries where the matches is more than 0 and the L1 and L2 properties are not equal. So that means we're we're getting rid of matches from a subgroup to itself. We're only looking at matches between a subgroup and other subgroups. And then we're going to use a transformation called lookup. And this is actually connecting the subgroup matrix data to one of our other data sets in this vega specification. So it's from our data subgroups, which is this data here with the sub-GeoJSON data, and that was the one that we used to create the paths for the subgroups, so to create those subgroup shapes and the name of the subgroup. And using the key properties.name and the values properties.center within our subgroup data, it translates from L1, L2 into two properties called source and target. So what this is doing is for each entry of the submatrix that we still have in our data set after we've done those two filter operations, it's going to look at that L1 property, which is going to be a subgroup name. It's going to compare the subgroup name. It's going to find that subgroup name in our subgroups data under the properties.name property, and then it's going to print out the corresponding center point as source and do the same for the L2, so the second subgroup in our matrix. Find the element in our subgroups data that has a matching properties.name value, and then print out the properties.center value as the target. So in plain language, what that's doing is looking up the subgroup 1 and subgroup 2 from our comparison matrix and finding out the XY coordinates of the center point of that subgroup that we've calculated earlier, and storing it in two properties called source and target, each one of which is going to be a pair of XY values. And then using those properties that we've just looked up, we're doing two geopoint translations using our projection, looking at the field source, and which has two values, so source 0 and source 1 is going to be the X and the Y coordinates, and then our target 0, target 1, and storing them as an SX and X and SY and TX, TY. So it's translating that center point of our group that we're hovered over and the group that we want the link to draw to, and turning them from geospatial locations in terms of latitude and longitude into XY coordinates of our drawing space. And then the final transformation takes those XY coordinates and joins them up into a line shape using the property, the transformation link path. So this is designed for drawing network diagrams, and it takes an X value, a Y value for a source, so this SX, XY value, and TX, TY value for the target Y, and we can specify, I've specified a straight line shape. We can also specify different kinds of curvy lines if you're interested. The Vega documentation has all of the details under data transformations. So that's the data all prepared to draw the links. To be able to show the links, there's another path mark just under our marks. Again, we've set the interactive property to be false, so that if we hover over the line, that doesn't remove the hovering for our shape property. We've retrieved it from the data pairs, and then we encode it to be on the enter. We draw that link path that we created. We draw it using the path property, which is its default location where that transformation writes to, and we've set the stroke to be maroon colored, and we've set the stroke width using a scale called line width, and that property matches. And if we scroll up to our scales property, we have that scale called line width. It's a linear scale that's just ranging from 0 to 35 and translating that into a line thickness from, if there's no matches, the line thickness will be 0, and if the value is, if there's 35 matching words, then the line thickness will be 15 pixels. And we've set it to be a little bit transparent using the opacity property. And then signals, the signal that we're using in this combined visualization is just that signal hover, and when we're hovered over a path, it gets updated with that subgroup data, and when we leave the region defined by that path, we go back to that subgroup being, to that hover value being empty. And what that does when we hover, that's going to redefine this subgroup matrix data based on the new filter property. So in short, we can hover over different areas and see how how Pama and subgroup languages being next to each other affects how many words matching between those subgroups. And we see some patterns that we might expect, like there's quite a few close matches between close subgroups compared to far away subgroups, but then we can also see some notable patterns, like some subgroups not seeming to have very many at all, whereas others have a lot, and also that some of the matches are between really far away subgroups. So that points us to an areas where we want to look at the data more closely and ask further questions about the data, about what those words are. Are there intermediate languages where, or language subgroups where those words are matching across a whole path of subgroups effectively. So I'd be really interested in hearing your thoughts about how we could take those questions and build a new visualization to answer them. And hearing your thoughts in general about building visualizations of language using Vega and Observable, or using other tools that you're interested in. I hope that you'll continue to explore these tools and explore the different types of visualizations that you can build. If you're coming to the CoEDL Summer School, it'll be really great to be able to talk about visualization with you in person and see how we can use different visualization design choices to set up a visual environment where we can explore and analyze data and discover new questions and start to find the answers to those questions about language data using visualization. This has been the video tutorial series for the CoEDL Summer School course on visualizing language data for analysis and communication. I'm Lydia Byrne. You can reach me through the comments on these video tutorials or through my Twitter at Lydia C. Byrne. And I hope I'll see you at the summer school. And if not, happy visualizing. Bye.